Sure. Yes, thank you.
Let me check, because I'm not sure Brian started the recording. I was trying to check that, but
I did.
Oh, you did. Okay, perfect.
Recording started here.
Okay. So the last talk of today and of the conference will be given by Boris Zilber, who will talk on the categoricity of pseudo-analytic covers.
Thank you. Thanks. I'm really happy to talk in this conference, specifically because it is Hrushevsky 60, and of course, what I would like to say that Hrushevsky has been, of course, quite a person in my life. I'm not sure that, the word person is right, but yes, as a mathematician and also as a friend. I think that we first got in contact sometimes around 85, maybe 86. It was a letter that I received from Woody, that he just said several things very nice and very encouraging for me. That he got interested in what I was saying at the time. And it has been really important that Woody take interest in some of my suggestions and speculations, indeed, and it is very specific for Woody that when he is interested in something, and he interested is in almost everything, really. And then, unlike many others, like with a relaxed attitude, like typical people, including myself, would say, oh, this might be a very beautiful idea and looks nice looking from this side and looking from that side, and but Woody once seen something interesting, simply goes for it and does it. Something that I would think was out of reach. And he comes and he does it. And so when I think that what is this attitude, except of course of a great talent and a huge technical capacity, it is also this. I prepared this line. It is Hilbertian like motto that wir müssen wissen, wir werden wissen. We must know, and we will know this. And this I think it is something very specific, and is a mark of really outstanding mathematician. Okay, so now I switch to the topic of my purely mathematical talk. And it is one of the very few subjects where I can work without fear of competition from Woody, because it is probably one where he hasn't expressed his hasn't published anything to the best of my knowledge. Although I presented some of this in our Oxford seminars and had a good portion of questions and useful criticism from Woody. So so there is some part of contribution from Woody here as well. Okay, so what I'm interested in is I'm looking at this picture of how an analytic, maybe universal cover of a complex variety is, but this universal in brackets means that it doesn't have necessarily to be universal. Just some kind of useful, nice covers with nice properties, and so we usually would think that there is this object on the bottom that is interest we want to cover, but there are many more algebraic varieties around, and so from these algebraic varieties we have nice, for example, étale coverings, or in classification in complex geometry, just unramified covers. Again, it doesn't have to be in the category of unramified covers. It can be in some nice, a different nice setting, and then on the top there is a not algebraic anymore, but some analytic object, and we have this this picture. So the typical example is this one that I mean, the most popular example is that it is a complex plane with some structure on it if you want, but you can also forget about structure and just think about it as a complex manifold for a time being. And then you have this exponential map going down. And this algebraic variety here is the complex torus, or in fact the same picture you will have if you start with a complex elliptic curve, and often the same notation is used, so it makes sense as well. Okay, so I'm thinking about this object, and there is obviously some, as I mentioned, some analytic structures there, but it is very different languages that we use speaking about objects of algebraic geometry. At least model theoretically, we more or less know how to formalize them. We speak about them as objects definable in an in this case, algebraically closed field. But what this structure should be? What is the formalism for this structure? And that's the main underlying question that I'm really interested. So so when I say this formalism, I want, of course, this to have some reasonable properties, and that would fall into nice model theoretic category. And so it should be stable, and when we talk about stable structures, it is also very nice to have a dimension notion, and the dimension notion, if there is one, there must be an agreeing with analytic dimension. This algebraic varieties must be part of this picture. So this multi-sorted picture in the previous slide. Of course, dimension-wise, this say if we have the cover, which is the complex plane or half plane, then this should be a kind of strongly minimal, or we can say quasi-minimal, because now it is abstract elementary classes or L omega 1 omega definable classes that we are talking about. The best picture would be that we could really say that our axiomatization in this or that form is uncountably categorical. And why categorical in this case is so crucial, except for its other nice properties, that it is actually a way also to say that we have a complete axiomatization. And this would be a truly complete axiomatization, because categoricity, of course, is ultimate completeness. Okay, now we immediately come into the problem of what should be the language on the cover. That would satisfy the desired properties or lead potentially to the desired properties. And then the first idea is that we look at this projective system. Well, it doesn't have really to be a projective system in general, but let's for the time being think about this being a projective system. And then it is very natural and of course very classical to look at the structure on U that is given by that comes from the algebraic sorts in the form of pro-definable relations, which means that so these are essentially positively definable types. And when I say type, I mean complete type. Well, now, because and at the same time, I only want to use positive formula or Zariski subsets closed in Zariski topology. So it is maximal positively definable types I'm talking about. Okay, it is actually a good idea, and it was already aired by Misha Gavrilovich. And the first problem with this, that we have uncounted many actually in all reasonable situations, uncounted many of such types, and which of them, but stability allows only, of course, only countable many, and so we have to somehow separate countable many of the possible uncountable many, and this is a problem of how you come into how you define. You have some abstract setting, and what is the criteria that this is the one that leads to a analytic subset on U or its Cartesian powers. And Misha Gavrilovich suggested a way of selecting such types based on algebraic topology, some criteria using algebraic topology, and proved under some assumptions that, for example, hold for abelian varieties, that if one does this selection using these assumptions, then we really get a stable structure. But the categoricity wasn't proved in that work. Okay, still it is it is not quite what works, at least not with me. And the alternative idea, somewhat alternative idea maybe, is to work to look for a complete family of analytic relations which give us some adequate picture of algebraic geometry that is adequate for this particular geometric setting. So if we deal with elliptic curves, then there is a theory of elliptic curves, and there are certain classical theory, there are certain notions, and obviously we want to include all these notions, and in fact, the proof of completeness would actually mean that the list of these notions, so what is written down in books, is complete. That if it gives us categoricity, then it means that they haven't missed anything. And in fact, it is a fact of this analysis of this theory that if, for example, when you work out the categoricity of an elliptic curve, the cover of an elliptic curve, and you miss pairing, then it is not going to be so your system of axioms is not going to give a categorical theory. And this is true for all cases. Right. So now very quickly some history of this. So first example, I started looking at so the exponentiation, the cover of the complex torus, and with some help of Martin, we made sense of it. And this case already required, of course, some model theory in the form of excellent quasi-minimal classes. So a little bit further than Shalast's theory. And also some arithmetic geometry, which when you look at the formulation itself, it doesn't it doesn't assume that you need to work with arithmetic geometry. And this is in the form of Kummer's theory and the Dedekind theory of Galois action on torsion points. Then the next example, the next case study was for elliptic curves. And Martin Bayes, using Misha Gavrilovich's, proved this the categoricity statement. And again, it required, of course, some arithmetic geometry now in the form of Kummer-Bashmakov theory and the Serre's open image theorem. And here is a good place to explain that when I say required, it is actually, at least in these cases, it is provable that from the fact that the corresponding theory is categorical, one can deduce the facts from arithmetic geometry, namely this certain particular statements that were involved here. And so, for example, Serre's open image theorem in the form that natural group of automorphism of the torsion points is actually a Galois group, up to a finite index. So it is the Galois group is finite index in here, and the difference is by given actually by this Weyl pairing. I mean, the Weyl pairing makes the difference between the natural group of automorphisms of this locally modular structure and the actual group, the Galois group. Okay, so then the next I mentioned is a study of cover of abelian variety. So it is successful, but conditional on either extension of Serre's open image theorem, which is not known, or it is provable. Yeah, this case is provable if you extend your language by introducing by making constant of all torsion points. Yeah, but so which is a really heavy cost. Okay, and then the first case of hyperbolic cover. Well, it was by Adam Harris and Chris Doe, but it was not the absolute version, but the version where you have to fix special points or CM points. And this is very similar to you fix torsion points here, or you fix CM points on this Shimura curve. In this case, well, in fact, you have to fix the special points on the cover, which are, of course, so because this H is part of the complex numbers, so in terms of complex numbers, you have, in terms of the field of complex numbers, you have quadratic points, quadratic over rationals, and they are inverse images of CM points, and I actually usually call them also CM points, which is not quite correct. Okay, so this is a situation that we have for a few years back. But now I come back to this and continue asking questions about this. Well, the questions are really you know, what is it all about, and what does it tell us about? So if we are successful in improving this categoricity theorem or pushing it somewhat further, what does it give us? Does it give it? Does it tell anything to algebraic geometers, and in what terms? And how far can we make very general conjectures that it is always the case? So what is going on here, and how much of model theory really is here? So these are all sort of questions that I'm interested in. Okay, so now an idea of somewhat better understanding of what is going on with this natural structure on the cover. So this idea here is that the better understanding here is that actually what we have in all the examples certainly is that we have here a fusion. Well, when I say fusion here, it is very much like Hrushevsky fusion, but in a very easy form, in a simpler form, where so far we are not going to use any dimension, non-trivial pre-dimension inequality. Okay, but later on we might, and. So actually, there are two structures here. The structure down below, which consists of all these algebraic sorts, and then the structures that we actually locate strictly on the sort U itself. So in our past examples, there were, for example, on the complex plane, it was the structure of the group, maybe with what comes from Weyl pairing, which is actually a small predicate, and so the structures that we actually allocate there are locally modular, and that's my expectation for other cases as well. Okay, and the axioms then would be simply what are the axioms for fusion, for a kind of trivial fusion, that we have to say that these analytic functions, they fuse together to rather explicit structures. Okay. And of course, then the formal pseudo-analytic structure on U is made of this pullbacks of Zariski closed relations, which is really principal types. And these guys, which actually are coming from non-principal types, these pro-definable relations, which are coming from non-principal types. Okay. And now we look at so now with the case study of this particular case, and this is this hyperbolic case, and because we want to use already what has been achieved. I restricted myself, and now I'm reporting on some work which is done joint with Chris Doe. So this Y's here are Shimura curves, and this is the traditional notation for Shimura curves as well. But in this picture, and that's what I want. I do ignore this so-called n-level structure. Now, I don't want to go into the detail what actually this means, but I simply say the following: that if you look at Shimura curve at some high level with n-level structure, then it would be defined over cyclotomic field of degree n, degree m, if I point at this. And the advantage of this, and actually what this n-level structure would mean, is that you have then also would consider definable the action of a group. Okay, so everyone probably knows that there is a classical action of those groups. And there is this action of a group of certain such group. It is actually SL2Z over a finite ring, and so the action of this group would be definable, but well, each element, action of each element would be definable. And I don't need it. And so I don't consider this n-level structure. And then the whole picture is defined over Q. Okay, that's important, that this whole picture is treated over Q. That's what it says here. Okay, so here is already rather rich structures that you see. And of course, there is already this suggestion that if we consider this H as a group, as a G set, so it is a kind of what we mean by G set is a kind of G module. So H with a action of G on it, then it is a locally modular structure that we can start thinking about. Okay, this is some beginning. Now the question, let's start doing some steps towards the proof of categoricity, and asking whether that's enough already that that our idea is going to work. So first we need to do certain model theoretic analysis, and this is actually some stability analysis. And to do this stability analysis, you need to understand some saturated model. Because you really, according to Sheller's theory, you need to understand which types are realized in models of your possible theory, and which are not, which are omitted. And to start this analysis, you need to construct this saturated model. although it doesn't have to be a very saturated model. And obviously the first thought and is to consider this projective limit. And then, of course, something also is going to happen with the group acting on H, and so this G tilde and gamma tilde are correspondingly what comes from GL to Q and SL to Z. This can be worked out, but it is actually not very simple. And a better way of calculating this saturated model is actually the classical Shimura-Adelic construction, and this goes as follows. So this take this X as H and well, made of two halves of the complex plane, except of course, except as you see you throw away the reals, okay, and now you consider this this formal set, but in the geometric setting, this because X is a complex variety, so you can also treat this as a kind of a multi-sorted complex variety, complex manifold, sorry, and then you also have the action of GL to Q. Here defined in some obvious way, and so this is a construction that can be used as a cover sort. And if you now factor it on the right by an open subgroup of this group of GL2 of Adels, so it is open subgroup would be of finite index, and so you factor by it, and what you actually get is this Shimura curve. So of course you can do it both abstractly, but also you can remember that there is this complex structure on X, and this would give you a complex structure on here, or in more formal terms on this object. So this is the classical Shimura Adelic construction. Well, I hope it is Shimura, but okay. Now our H tilde actually can be obtained from this big covering sort by factoring over some closed subgroup which is not open actually, and so it is of infinite index, but it is something that so it is some diagonal subgroup. Never mind this, and so we get this object, and it is more convenient way of understanding this object as a factor of this. And also our G tilde would also be understood as what you see this this full group. It acts on S, but its action on H tilde is hampered by the fact that H tilde is So you spoil it by factoring by this delta. And so the actual action is actually by a smaller group. A nice action is by a smaller group, but then there are also some other problems of identifying which of the embeddings really. So the action, while in the previous in this setting the action is kind of zero definable. So this action on here is not zero definable, but it can be actually analyzed. It can be understood. Right. So the picture that now we get it is this one. Okay. I have what, 3 minutes?
Yes.
Okay. And then what we do, we say that the study of this is actually can be reduced to the study of this with a bigger cover, and then we define what we call a pure structure on this adelic structure S. So it is just the set with the action, but also with the splitting into what in topological terms would be connected components. And there would be as many of them as elements in this. Well, actually, this is isomorphic to that group delta. And each of these irreducible components is going to be isomorphic to this H. So this guy, this covering guy, actually is infinite many leaves. Each of them is isomorphic to this one. Yeah. And then the action of elements of G on here is very nice. It is zero definable. And then there is also the equivalence relation, which is actually definable here. It is that 2 points are in the same component of S. And the full structure, we write it as full, is the one that takes into account also all the algebraic sorts with all this Zariski topology on it and the field present there. Then there are special points, of course, and the special points on the top are fixed points. And the images of these special points are CM points on the curves. Well, I actually call this also CM points. And then our question about types, right? So we have to understand what are the types there, and then to decide which types belong to H or to formal equivalent of H. And to understand the types, we need to understand the action of the of this group, the automorphism of the field. So how it acts on this S, and in particular, actually how it acts on special points. Just like in Serre theorem, we needed to sort out this question for torsion points. And it turns out that well, this is quite a non-trivial problem, and this problem was formulated by Langlands actually soon after he formulated his big program. And it somehow it is connected with this, not directly, but it does connect it. It is connected, And the formulation is quite tricky, so I'm not going to try and reproduce it here. But the fact that he called his paper, he put this word "ein Märchen," which means a fairy tale. So when he formulated this, he considered it very important to that the guesses that he made are really so excitingly true. Well, it turned out that it was not very far from what known, and by 82, 83, this was resolved by actually Delin, Borovoi, Milne, and Shea. Yeah, so it is a general case. We actually need it for product of Shimura curves. And this involves quite a serious class field theory. Of course, that includes also this Artin reciprocity law that gives a connection between, gives this surjective homomorphism from, well, actually it must be the group of ideals, the invertible elements from here. Okay, and so when we manage it to kind of digest all the technology and understand it properly, and so on, this actually is quite non-trivial, at least for us. So what is we have two statements now. So first is a pure Galois statement that says that so we have so this is as you can see here, some locally modular structure. So it is a bit more than just the locally modular structures that I explained on the previous slide. It is not just the action of GL2 of adels together with the splitting. There is something else to be added here, and what you have to add are the cases of unlikely intersections, actually. So you have to consider that you cannot move certain things because they are fixed by the intersection with wrong varieties, with non-special varieties. Okay, and but once you do, and this was something that we missed in our first version, and so on archive there is a wrong version now. So the right version is this one. And once you work it out, then it is more or less straightforward that you can write down, well, it is exactly this system of axiom as I described. So I call it this. So you have to explain a fusion between this structure, yeah, and this is a structure on the upper half plane that actually corresponds to this relation, right? And the curves. And so this turns out to be categorical, and the proof goes through more or less traditional steps. Also using the results of Adam Harris and Chris Doe. So this is the main risk. Maybe I can show here one more slide. So it is now pure speculations. Well, you see, in in this historic slides, I told you that once we prove categoricity, we actually can also prove that the arithmetic geometry that we have used actually follows from the categoricity statement. So here it is more complicated. Actually, this statement of conjugacy conjecture is quite complicated, and so that's a main abstraction maybe. But I believe it is possible, and in some sense, I believe that formulation of this is very transparent, at least to us model theorists. What these axioms. And because in the setting of these geometric people, they think in different terms. So that's why it's so convoluted, this statement of conjecture. And there are many versions in literature, and people split it in parts and explain different parts in different terms. And then if it is possible, then, it simply means that extension of this categoricity conjecture would actually mean that proving or even formulating a categoricity conjecture is a way of formulating conjectures of this kind. Of the kind that, at least for a huge category of Shimura varieties, Langland formulated, but there are much more around there. And for example, we can also ask, can we? So this H can serve as a nice cover for many curves. And so now, can we? Is there a kind of a maximal structure on H, which would give us a truly full pseudo-analytic formalism of what H is, so that this is categorical? Okay, and that's all. And sorry if I went over my time. Thank you. Oh, I did.
Thank you, Boris. Are there any questions?
Well, I'd like to say thank you. I appreciate very much this talk, and it looks like very, very beautiful material behind it. I have some various questions, but one, as you said, I never looked at abstract elementary classes, and I don't feel completely comfortable. How do you get just this subjectivity? So I guess the categoricity implies in particular that any uncountable model of this L omega 1 omega sentence, in particular, it should map, somehow the upper half plane should map onto not only individual curves, but also to the projective limit. So how does that happen?
No, it doesn't say that. Well, you see, the projective limit would require that your cover is saturated. If you are talking about a saturated version of the cover, then of course what you said is true. You see,
but precisely if you say categorical, doesn't it imply that they're all saturated to some extent?
Sorry?
No, but you said categorical. So if there's one which is saturated and one which is not, I mean, it should follow.
No. It is categorical in the formalism of abstract elementary classes. So it is when I say saturated, I mean saturated in first order sense, and in
so it's not an L omega 1 omega sentence.
No. no, yeah. So what is so what you ask is, so this H tilde, indeed H tilde does contain the projective limit of this system, right? So it is actually equal to the projective limit of this system. But if it is H, which one is not arbitrary?
I think so H tilde is the projective limit by definition.
It is a projective limit for this given system.
Yeah. But I guess I'm talking about the map from S to H tilde.
Say again, I didn't hear you well.
So is the axiomatization in L omega 1 omega?
No. This is not this is not axiomatized by L omega 1 omega. This is the first order analysis. You see, the model of this is a model of L omega 1 omega. This one, when you have H here. So this is a model. And there are models in other cardinalities, but the version with H tilde is not a model of L omega 1 omega theory. It is not. So they're different. Mm-hmm.
So it's a different logic. Okay.
Yeah.
Okay.
I have a question about what you were saying towards the end, where you were suggesting that there may be some way to recover, you said Langland's conjectures, not quite sure exactly what you had in mind of Langland's program. Did you mean things like the fundamental lemma, the identities of orbital integrals? You should see those as being consequences of categoricity of these structures? Or are you talking about the earlier Langland's conjecture about the components?
No. It is you see if you mean Langland's program, yeah, because this is so what this is Langland's conjugacy. So it is so this one is called what? The conjugation of Shimura varieties conjecture, and this was several years after he formulated his program, but they are related, and in particular the relation can be already seen in this the basic picture. You see, what Langland's program is about is that you have on the one hand side you have a representation of the Galois group, and we have seen the role of Galois group here, right? And on the other hand, you have the representation of this guy. In this case, it is GL2 of Adels on by its action on automorphic functions. And these guys, they are automorphic functions, right? So when GL2 of Adels act here, you represent, you see how it acts on this automorphic functions, and so in this picture, you see, it is interesting point that you start with purely analytic picture, and somehow Galois theory and representation of Galois groups really play here very important role. And also you have this heavily involved in this the action of this adelic group. So I'm not saying that that it is the same, but you know, there are these relations, and there are many commentaries about the links of this Langland's conjugacy conjecture, conjugation conjecture, and his program. So it is a kind of toy model maybe of the big program.